Hey, this is Mr. G, and we're going to do some problems involving Newton's laws. All right, so here we go. Here's problem number one. Here's a block sitting on the ground. All right, and let's say this thing has a mass of 2 kilograms. And there's a force acting on it this way. This could be a rope tied to it. It could be somebody pushing it. It could be a rocket engine strapped on it. Who knows? It's a force. And let's say that that force is 5 newtons. All right, and there's also friction, okay? Friction, that's between the box and the floor here, but I'm gonna draw that arrow right here. And I'm gonna use a lowercase f to stand for friction, so. Friction, and then this is an applied force, okay? And this block has an acceleration. That means it's gaining speed here. So let's say that it's accelerating at a rate of 2 meters per second squared. So it's going faster and faster and faster, right? And it started from rest. So then the question is, how large is friction? What is this friction force acting on it so that this 2 kilogram block accelerates at 2 meters per second squared? So I'm going to draw a couple of other arrows because there are 2 other forces acting on the block. They're not relevant to solve for this problem, but we should get used to drawing them anyway. There's the weight of the block. That acts straight down, and that's the force of gravity on the block. And then the way to calculate weight, we've talked about this. It's the mass of the block times little g. And then the floor is pushing up on the box or the table or the road, whatever the box is sitting on. There's an upward force acting on it. If there was no upward force acting on it, it would be sinking down into the ground. But it's not doing that. And that force is called the normal force. That normal force, the N means perpendicular to the surface. Okay then. So then, how am I gonna, I'm gonna figure out what this friction force is. So you know what? I'm going to write down Newton's second law, which says net force is equal to mass times acceleration. And then the next thing to do is to look at this picture and figure out what am I going to write here for this net force expression. All right. And so the forces here that are involved for this problem, it's going to be, there are 2 forces. There's this force pulling it towards the right, and there's this frictional force. It's like a drag force, essentially, acting on it towards the left. And in our coordinate system, this way is positive, and left is negative. So what I'm going to write here is the applied force, F, minus friction. That's the net force. That's how I write that out. It's this guy minus this guy. And that's equal to MA. So, if you want to, you could plug in numbers now, right? We can do that. So let's see. So we're going to have the applied force is 5 minus F is equal to, so M is 2 and acceleration is 2. So it's equal to 2 times 2, and I'm leaving my dimensions off here, which is bad. I shouldn't be doing that. So that means that 5 minus friction is equal to 4. What number is that? If you said 1, then you're right. That frictional force must be 1 Newton. If you want to do this in terms of the math here, we could certainly, How do I get friction by itself? Well, I'm going to add F to both sides. So plus F, and I'm going to subtract 4 from both sides. All right. And then so what does that do? Well, that means that this friction term here cancels out. 5 minus 4 is 1. And likewise, these two guys cancel out. So that frictional force is 1, and the dimension here is a Newton. So friction is 1 Newton. There you go. Okay. And remember, you can re-watch this little video as many times as you like. I would recommend re-watching this several times until you fall asleep, which won't take long. All right, here's problem number 2. I have a string hanging from the ceiling, and it's holding up a box. Lots of boxes here. Okay, and that box has a mass, M, of 2 kilograms. And it's just sitting there from the string, not doing anything. It's hanging from that string, motionless. So the 2 questions we want to ask are, one, what is the weight of this box? And question 2 is, what's the tension in the string? So weight and tension are 2 forces we've talked about. The weight of this thing, that is the force of gravity acting on it. So I'm going to draw these forces by using little arrows. So there's the weight, and that is equal to mg. And then tension, that's the name we give to a force exerted by a string or a cable or a rubber band. And that force is acting straight up, and I'm just going to use a T to represent that tension force. And, well, one of these forces is pretty straightforward here. The weight of an object, it's m times g. So here, that weight of this object is going to be 2 kilograms times mg. We're going to use about 10 meters per second squared. And so 2 times 10 is 20. And a kilogram meter per second squared is also called a Newton. So there's the weight of this thing. It's 20 newtons. It's a force. Next, what's the tension in the string? Well, I know that if this box is just sitting here, it's not going anywhere, it's not speeding up, it's not slowing down, it's not turning, that means that the acceleration of this guy is 0. And I know some of you can just look at this and immediately, boom, know the answer. But yeah, you could work this out and analyze this using Newton's second law. And that says that net force is equal to ma. So here, the way you write out the net force, I'm going to say that down is positive, just for fun. So then the way I would write these 2 forces is mg minus t. Wait a second here. Let me redo that g. mg minus t is ma. But guess what? The acceleration is 0. And anything times 0 is 0. And so this whole thing, bloop, is 0. And so if mg minus t is 0, well, that means that 20 newtons minus t is 0. Yeah, t's got to be 20 newtons. There you go. T is 20 newtons. If something is not speeding up or slowing down or turning, the net force on it is always going to be 0. Okay, one more. Problem number 3. Okay, let's say that we have here's a car zipping along, a model car. So it doesn't have a whole lot of mass. Let's say that this guy has a mass of 5 kilograms. All right. And it's accelerating. All right, so it's gaining speed. So what forces are acting on the car to make it accelerate? Well, the forces acting on the car, for one thing, the car has weight. So there's mg. And there's also a normal force acting on the car. That's the road pushing up on the car. And I know there's a normal force on each of these sets of wheels here. I'm just going to draw that force like this. So there's your normal force. And those two guys in this problem, those are equal to each other. Because the car is not accelerating up or down. It's accelerating towards the right. So then what force is pushing the car towards the right? It's going to sound crazy, but it's friction between the tires and the road. So I'm just going to draw that right here. So friction. Friction not only can slow things down, it can speed things up. So yeah, there's friction between the tires and the road. That's causing the car to accelerate. And then the other force acting on the car would be drag. Right, and that's from wind resistance, for example. Or there's friction between the axles and the wheels of the car. And so then, what is it that I want to find here? I have no idea. Well, let's say that the force pulling the car forward is 20 newtons. And the friction force acting on the car, the drag force acting on the car is 15 newtons. And we want to find out what is the car's acceleration here. So there's a force of friction between the tires and the road, and that's pushing the car towards the right. And there's a wind resistance, it's drag trying to slow the car down. That's towards the left. So I'm going to write down Newton's second law. Net force is equal to ma. And the net force here is going to be that frictional force minus the drag force is the mass of the car times its acceleration. So we can put numbers in here now. So friction is 20 newtons minus the drag force is 15 newtons is equal to the mass of the car, 5 kilograms, times the acceleration of the car. Now it's turned into a math problem. So on the left, 20 minus 15 is 5. So I got 5 newtons is equal to 5 kilograms times A. And now I want to get the A by itself. I divide both sides by 5 kilograms. Okay, so 5 divided by 5, it's 1. And believe it or not, a Newton divided by a kilogram is a meter per second squared. And then 5 kilograms over 5 kilograms is just 1. And so, problem done. The acceleration of this car under these conditions is 1 meter per second squared. And that's good for now, okay? Have a great day.